Okay, hi everyone. So in this video, we're going to be looking at some questions involving the contraction mapping theorem, also known as Banach fixed point theorem, and also some results involving compactness. So compact sets, compact metric space. Okay, so in this first question we want to answer, we're given the set X to be the closed interval minus 10, 10, which is a subset of the real numbers, with the standard norm or the standard metric, that's just the modulus, and a function from this interval in 2R defined by f of x equal to the square root of x squared plus 1. And we need to answer these three questions. So the first one is, using the mean value theorem, we want to prove that for any 2 points in x, the modulus of f of x minus f of y is less than or equal to this constant multiplied by modulus of x minus y. In other words, this will, if you recognize this, this is the Lipschitz condition, or f will be uniformly continuous, if you could show this. The second one is to then prove that there are no fixed point of this function f. And the third one is asking, does this result contradict the Banach contraction theorem, or Banach fixed point theorem, or sometimes it's called contraction mapping theorem? There are a bunch of different names for this result, and we need to justify our answer. Okay, so the first thing is we want to recall a couple of things. First of all, what is the fixed point? What is the contraction mapping theorem? And what is the mean value theorem? Okay, so maybe we should start there because it's talking about mean value theorem. So recall. So the mean value theorem is usually written like this. Let f be some function on some closed bounded interval AB into the real numbers, and f is continuous, so let f be a continuous function on AB, right, on closed interval AB. Maybe I should have put what is this? So let me do that. Right, so we are recalling this is the mean value theorem. It's the same one you would have learned if you did a first year calculus course. Okay, this is mean value theorem, so let f be a continuous function on closed interval AB, and it has to be differentiable on the open interval, and differentiable on the open interval AB. Of course, if we look at what this function f is, it's basically a square root function. So, you know, the square root function is a continuous function, and the square root function is C1, meaning that it is differentiable. Okay, so this function f satisfies these conditions, and differentiable on open interval AB. The mean value theorem tells us that there exists some, let's call it xi, in AB. I think it's open interval AB is the xi. Such that this equation holds, which is the derivative of f evaluated at psi is basically the mean of the function between these 2 points. So it's like the average of the function, or you could think of it like a gradient. Basically, there's some value xi in between A and B that gives you the gradient of the chord connecting the points A and B. So that gradient is given by f of b minus f of a. So that's the change in the y over the change in the x value. Okay, so that's the mean value theorem. And okay, so we just need that for the first part. So let's try the first part A using this. So I want to use this mean value theorem to show that I could bound the function values or the difference in the function values. Basically, we're showing f is Lifshitz continuous with Lifshitz constant 10 over square root 1 of 101. So let's go down a bit. Okay, so my function f is, so let f of x be the function, it's square root of x squared plus 1. Okay, and if we're using the mean value term, so I'll just put over here that f is continuous since x squared and square root x are continuous functions. Okay, so what you see is basically decomposition of continuous functions, which is again a continuous function. So since these guys are continuous, and f is also differentiable. Okay, f is also differentiable on this interval. So let's find its derivative. Okay, so let's see if we can find its derivative. So it's x squared plus 1 to the power of 1/2. Okay, so this means the derivative of f, right? So this will just be 1/2 x squared plus 1, and then I subtract 1 from the power, so it's down to minus 1/2. And I need to multiply by the derivative of what's inside here. So that's 2x. Okay, so this simplifies down to x over square root x squared plus 1. Okay, so this is, the derivative is x over square root x squared plus 1. Okay, so you see it is differentiable because here is the derivative. And what could be the only thing that could go wrong with this derivative? Well, when the denominator is equal to 0, that's when something could go wrong. Now remember, this function is defined on closed interval minus 10 to 10. So there's no value in this interval that you could plug into that denominator to make it 0. In other words, that denominator is never going to be 0. Okay, so there's no problem with the derivative. Essentially, that's what I'm arguing. There's no problem with this derivative. Okay, so that is f prime of x. Something we'll need to know or we'll need to observe is that this function f prime of x, so if we just view this function as any function, any new function, let's call him g. Okay, so this is just some new function. This function is increasing. This is an increasing function. Meaning, well, it's increasing, I should say, on the domain minus 10, 10. Okay, how do I know this function is increasing? So what you will have to do is differentiate g. So you'll have to find g prime of x and show that g prime of x is always bigger than 0. In other words, the function is always increasing. The values are always getting bigger. And why is that important? Because if a function is increasing and it's increasing on this interval minus 10 to 10, then if I want the maximum value of this function on this interval, it will occur at the rightmost point. Okay, because it's increasing. So if it's increasing between minus 10 to 10, the maximum value will be when you plug in the rightmost point. Okay, so that's just an observation. Of course, that's easy to show. You just differentiate this thing again. So in other words, f prime of x, which is what I was calling g of x, you could look at it as f prime of x, that's fine. So g prime will just be the second derivative of f. So this f prime of x is increasing, it's an increasing function. Now we're going to invoke the mean value theorem. So from the mean value theorem, there exists, so there is some xi in open interval minus 10 to 10, okay? Such that, actually we can actually put a closed interval in this case. Anyway, such that, so it is f prime of xi equals, so it's f of e minus, okay, so maybe let's not put an interval. Let's keep the interval there general. So let's just say there's just some xi. Of course, we will eventually choose a xi within this interval. There exists some xi. So what I'm saying is I'm going to just write this for any general function, any general interval, some xi between a and b, such that this guy is equal to just f of b minus f of a. So instead of b and a, we could take x and y. Yeah, maybe that's what I want to write. There's some xi in x, y. Yeah. So here's f of x minus f of y divided by x minus y. Now I'm just going to cross multiply. So I get f of x minus f of y is equal to f prime of this mystery number xi, x minus y. And now I'm going to take modulus on both sides, because if you look at what we have to prove something involving the modulus. Okay, so for any x, y, and x. So any x, y, and x. So of course this interval, these x, y, x comma y belong to x, which is minus 10 to 10. So let's take the modulus on both sides. And this is the modulus of the product, so we can break it up into two products. So the modulus of f prime of xi by the modulus of x minus y. So it's almost what we have to prove, but I need to get a bound for this derivative. So here's where that observation that the function f prime is an increasing function. So if it's an increasing function on the domain x, which is a closed bounded interval minus 10 to 10, then what I'm saying is, let me write a little note, since f prime is an increasing function on its domain, which is minus 10 to 10, okay, that means that any value of x of f prime, okay, will be less than or equal to its value evaluated at 10, the rightmost point. Okay, because if it's increasing, then all the values will be less than the endpoint value. So I'm going to just sub this into 1. Okay, so sub into 1. gives modulus of f of x minus f of y is less than or equal to f prime modulus of f. Well, f and f prime are always positive, so we don't need the modulus, but I'll leave it in. Then modulus x minus y. What was f prime? Well, we worked that out earlier. F prime is x over square root x squared plus 1. Okay, so f prime of 10 is x, so that's 10 over square root x squared, so that's 10 squared plus 1. Okay, and this is 10 over square root 101 mod x minus y. Okay, so that's what we wanted to prove. So we proved that that is f is Lipschitz. So maybe I should say is a contraction map, right? Because a contraction map is a Lipschitz map if the Lipschitz constant is strictly between 0 and 1, right? This guy here is less than 1. So maybe let me write that a bit better. So since 10 over square root 101 is strictly less than 1, f is a contraction map. Contraction mapping. I could just say it's a contraction map. Okay, so that's the first part that we wanted to prove. So we proved this bound, and since we know that the Lipschitz constant is strictly less than 1, it's a contraction map. Now, the next part is they want us to then show that there are no fixed points. So what a fixed point is, remember, a fixed point simply means f of x equal x. So let's assume that there is a fixed point. So assume f has a fixed point. Let's just call him p. Okay, so p is some fixed point. Then that will mean, by definition of a fixed point, that means f of p equals p. That's what a fixed point means. But what was f? F was the square root of x squared plus 1. So the square root of p squared plus 1 equals p. So if I square both sides, I will get p squared plus 1 equal p squared. So that means 1 equals 0, which is a contradiction. Right? Therefore, what we assume was wrong. So I assume f had a fixed point. So therefore, f has no fixed point. And part C is asking us, does this result contradict? I think it was there. Does the result contradict Banach contraction mapping theorem? So obviously it's not going to contradict the theorem, okay, because it's a theorem. The theorem will always hold. But essentially what it's asking is, why is the result from this theorem not true? So to see this, we just need to write down what was the fixed point theorem. We call contraction mapping theorem or Banach fixed point theorem. Okay, so it's something that's called contraction mapping theorem. right? So what this is saying is we need a complete metric space. So let X be a complete metric space. And we have some function from X into X, which is a contraction mapping. Or a contraction mapping. Then F has a unique fixed point. So only one fixed point. Right? So that is what the contraction mapping theorem says. So we showed in the first part that our F, okay, so we showed that our F, this F is indeed a contraction map. Okay. But we then showed that it has no fixed point. And of course, the space we are in is R. So well, it's a closed, so X is a closed subset of R, and R is complete. So any closed subset of a complete metric space is also complete. Let's write down all of that. In this question, okay, F was a contraction mapping. Okay, so F was a contraction mapping. Also, X, which was defined to be the closed unbounded interval -10 to 10, which was a subset of R, is a complete metric space. Since X is a closed subset of R. So it's actually a complete subspace, but it's still a metric space. Since X is a closed subset of R, and R is complete. Okay, so R is a complete metric space, but the space we are working in is X. Okay, it's a subset of R, but since X is closed, any closed subset of a complete metric space is itself a complete metric space. So X was a complete metric space. So if you look at Banach fixed point theorem, it seems that we should have gotten at least a fixed point because we have a complete metric space and we have a contraction mapping on it. So what went wrong? The problem here is, so maybe I should say instead the reason instead of the problem, the reason why this theorem did not work is because F does not map X into X. So in order for the theorem to work, F needs to map X into X. So if this is true, then F needed to take the closed interval -10, 10 and map it into the closed interval -10, 10. But I claim that this is not true. F is taking this closed interval and it's mapping it to something outside of this. It's mapping it to, let's just say, the real numbers. So I need to give you some point in the domain that is mapping outside of it. Okay, so for example, so I know F is increasing, so let me just take the endpoint. For example, take X equal 10. Then F of 10 which is square root of 10 squared plus 1, square root of x squared plus 1, which is square root of 101, right? So this is certainly bigger than 10. Therefore, this guy is not an x. So F, yes, it is a contraction map, and yes, the space X was a complete metric space. The problem was F was not mapping X into X. It was mapping X into a bigger space. So that's why this theorem did not work, or you cannot apply this theorem in this case. Okay, so in this next question, we're going to look at you could think of it like an extension of the Hausdorff property for metric spaces. That is, if I have two disjoint compact sets in a metric space, then there exist disjoint open sets, GA and GB, which separates these two sets. So A is contained in J and B is contained in G of B. Okay, so the picture, let's see if we can draw a picture. So here's X, and I have two disjoint compact sets. So compact is closed and bounded. Okay, but the converse may not be true. So here is A, and here is B. Okay, so these are disjoint compact sets. What this is saying is that in a metric space, we could then find two disjoint open sets. So this guy here is GA, and this guy here is GB. Okay, so GA contains A and GB contains B, such that these open sets are disjoint as well. Okay, so these guys are compact. This guy is compact. This guy is open. This one is open. Okay, so that's what this result, well, the first part of this result is saying, and then the next part is, we'll then prove that the distance between these two sets is strictly positive. There are a couple ways to do this. One of the easier way is we're going to basically use the distance between a point and a set. So if you recall, the distance between a point X and a set A is the infimum of all distances between this. So in this case, X is a fixed point. So X is fixed, and I'm going to measure the distance from X to every point in A. And all of these distances, I'm then going to take the infimum of it. Okay, so we saw this before. This is the distance of a point to a set. To set. Okay, and in the second part of the question, they are asking about the distance between two sets. So that's like a generalized version of this. So in order to use this one, I claim that this function is continuous. So let me write down a bit more precisely what I mean by that. So I'm going to define. So let's define first. So this proof, I'm taking it in two parts. The first part, of course, I could just say that this function is continuous and just use it in the proof. But let me go through the proof that this function is continuous. So I'm going to define a mapping. Let's call him phi. Let me write that better. Define phi from x into r phi. So phi is going to sometimes this is written like phi sub a to emphasize that it is like with respect to the set A. Okay, we can keep it like that. So it's going to be defined by, so it's going to take an element in the metric space X, and it's going to map it to its distance to A. Okay, so you can imagine you could vary the set A and you will get a different distance. So all this is doing, it's taken every point in the metric space and as an input, and the output is a number, right? This is just a number, a real number. And what is this number? It's measuring this point, the distance from this point to this set. Okay, so that's what this mapping is doing. And I claim that this map is continuous. Okay, so that's my claim. So I claim that phi of A is continuous. Okay. So let's prove that it's actually Lifshitz continuous. So it's actually uniformly continuous, as we'll see in this proof. So we could, for example, say for any 2 points, x and y, in a metric space X, by the triangle inequality, okay, so by the triangle inequality, the distance from X to a point A, so this point A will be in the set A. So I'm just applying triangle inequality. So instead of going from X to A, I'm going from X to Y, and then from Y to A. Okay, and this is true for any element of A. Okay, so this is just triangle inequality. Now I'm going to take the infimum on both sides. So I'm taking the infimum over, since this is true for all points in the set A, I'm now going to take the infimum over the set A. Okay, so I could say taking the infimum over all points in A. Okay, so taking infimum over all points in A. So this guy, if you take the infimum of all of these distances over every A in the set A, that is just the distance from X to A. What is it? It's the infimum over all dxa, where A ranges over the set A. So this guy becomes the distance. This is just the distance of X to the set A. Less than or equal. And dxy, so that doesn't have any A in it. That remains the same. And this one, well, this is just the distance from the point Y to the set A. So that just becomes the distance of Y to the set A. Now, if you're thinking, okay, well, I started this proof by saying let X and Y be any 2 points in the metric space X. So it could be that X or Y are also elements of A. Then wouldn't this also have an infimum in it? Well, yes, but if you think of it, if either, let's just say X, let's just say X happened to be an element of A, and I'm taking the infimum over all points in A, then this guy over here, if x is an element of A, I could just set A equal x, and the left-hand side will be 0. So the inequality will be satisfied. Same thing with y. Okay, so yes, it could be that x and y, yes, they can be elements of A, which means when you are taking the infimum over A, that this term here can change. But if x or y happen to be in A, this inequality is satisfied. Because what happens is you just get 0. Right? You just get 0 for everything. Okay, so if you want to, you could sit and think about why that is true. What happens if x is in A or if y is in A? Then this guy here will be 0. And of course, 0 is less than anything, less than or equal to anything positive. And if y is equal to 0, then this guy here will just be 0. And you just get dxa is less than, the infimum of dxa is obviously less than or equal to dxy, since y is in A. Okay, so take an infimum, we get this inequality, and I'll call this 1. Okay, and similarly, if we interchange x and y, or if you want to, you can think of it like, yeah, interchange in x and y. I could get this one, dy a less than equal dxy plus dxa. Okay. Now from 1 and 2, we could combine 1 and 2 to get if I combine 1 and 2, then I think it's easy to see that minus dxy, right, is less than or equal to, so I'm using part 1. I'm using the first one, and I'm taking this guy on this side and this one on this side. So that's equal to this one. Oh, sorry. With this one, I'm using the second one. I'm taking this on this side, so it becomes minus dxy, and I'm taking this on this side. Yeah, so it would become minus dxy is less than or equal to dx of A minus dy of A. And now I use the first one, and from number 1, I could take this one on this side, and I will get this guy is less than or equal to dxy. And so I'm just rearranging those inequalities. And this inequality is just the modulus. Good. So this is the same thing as saying that the modulus of dx a minus dy a is less than or equal to dxy. Right? But what is dxa? dxa is just phi a of x. And what is dya? That is just the function phi applied to y. Remember, phi is the function that maps a point to the distance from that point to the set A. Okay, this is less than equal to dxy. Right, so the Lifshitz constant here is 1. Okay, this is uniformly continuous. So phi xa is uniformly continuous. which imply phi A is continuous. Okay, on X. Right? Because remember, how did I get this is uniformly continuous from this line? Well, this is just what is the metric in the codomain? So phi is mapping from X into R. The metric in X is D. The metric in R is modulus. So if I want to show phi is uniformly continuous, I need to show the modulus of phi X minus phi Y, that's the metric in R, is less than or equal to, well, it's less than or equal to epsilon whenever d of xy is less than, not less than equal, less than epsilon, when d of xy is less than delta. So you could just take delta equal epsilon. Okay, so this thing is continuous. Right, so yeah, so that was my claim, verified there. Now we could go on to the main part of the proof, which was how if you give me two disjoint compact sets A and B, how do I construct an open set containing A and an open set containing B, such that these open sets are also disjoint? Example here now to show the result in part A. Okay, so to show the result in part A, I'm going to define, until again, this should look familiar to you, the distance between these two sets, A and B. Okay, so essentially what I'm doing is these two sets, I'm getting the distance between them. So this thing here, this is the distance between A and B. So I'm going to define the distance between A and B. So you remember what it is. It's just the infimum. So it's a generalization of that distance function we just showed was continuous. Is the infimum over all distances between A and B, where A comes from A and B comes from B. Okay, so it's the infimum over all of these distances. And so since A and B are compact, this implies, so compact implies closed. A and B are closed. Also, and what do we know? Also, A and B, we are told are disjoint. Okay, so A and B are disjoint closed sets, which means limit point of A is not in B, and any limit point of B is not in A. So they don't have any points in common, and they don't have any limit points in common. So therefore, we can say thus. The distance between A and B is bigger than 0, strictly bigger than 0. Remember that the distance between A and B equals 0 if Well, if A and B are not disjoint, or it could be that one of them contains a limit point of the other, or B is a limit point of A, or maybe this A is a limit point of B. Okay, so basically, in order to get the distance between these two sets to be strictly positive, they must be disjoint, but also they cannot have any limit points in common. They cannot share any limit points. Okay, they have to be separated sets. Okay, but we don't need that definition. Okay, so the distance is strictly bigger than 0, and I'm going to let this distance, I'm going to call this distance delta. Right, so I'm going to define this distance to be delta. Right, so now we know why it must be strictly bigger than 0. It cannot be equal to 0 because they are. So if it was, for example, that A and B, if we didn't know whether A or B were closed sets, it could be that this distance was 0, even though they are disjoint. Because what could happen, maybe one of the limit points of B was contained in A. Because remember, limit point may or may not belong to the set. So A and B could be disjoint, yes, but maybe A had one of the limit point of B. In that case, the distance between them would have been 0. Okay, so you need to make sure they don't share limit points, and the fact that A and B are closed and disjoint means they are disjoint and they don't share limit points. Okay, so just so that's why there's a lot of thing going on by simply saying that this distance is strictly positive. Okay, so now I'm going to try to make these two neighborhoods. So this guy is what I define to be delta. Okay, so I'm calling this guy delta. Now I'm going to define GA and GB. Right, let's see how to define GA and GB. So we're going to say, for example, let GA be the set of points in the big space X such that the distance between those points and A is strictly less than this delta over 3. Okay, and GB in a similar way. We're going to define it to be all the points in the big set such that the distance between those points and B are strictly less than delta over 3. Okay, so I define these two sets, GA and GB. Now I need to argue why is it that A is contained in GA? Why is it that B is contained in GB? And why is it that GA is open? And why is it that GB is open? So why are these open sets contained in A and B? Okay, so that's not quite obvious. So first, let's tackle down. Why are these open sets? Why is J and GB open? So now comes what we just proved here, that the function phi A is uniformly continuous, which means it's continuous. So this function is continuous. So let's see. The sets GA and GB are open since they are the pre-image of open sets. Well, what is the open set? It is since, so I'll give you since GA, so you have to think about why this one is true. Since GA is equal to, I claim is equal to the pre-image of this mapping, phi A, which is the same map that we just looked at here. Right, so remember, phi A is this mapping. It takes this X and it measures the distance between X and A, right? So this is a map from X into R. So I claim that GA is the pre-image of a certain set in R. I claim it is the pre-image of this set. Let's say on the point. So we also know that the distance, right? The distance is obviously less between 0 and delta over 3. Or if you want, okay, we'll take that. I claim it's a pre-image of minus infinity to delta over 3. Okay, so minus infinity comma delta over 3. This is an open set in R. And I know phi is continuous. Phi A is continuous. So it's the pre-image. So GA is the pre-image of an open set under a continuous function. So GA is open. Since GA is the pre-image of minus infinity delta on 3, right? It's everything that maps less than delta over 3 of this, which is an open set. Open intervals are open sets in R. Fun open set in R, and phi A is continuous. Okay, so that's why we needed to know that this mapping phi was continuous, because we are going to define, when we define GA and GB in this way, I need to argue somehow, why are these sets open? So if I could show they are the pre-image of open sets under a continuous function, then they will be open as well. Okay, and same thing for GB. Similarly for G of B, right? So G of B is the pre-image of phi B, which measures the distance between any point and the set B of the same set, minus infinity to delta over 3. So A and B are open. Okay. So now the next part is, why is A contained in GA? Why is B contained in GB? Okay, so very easy, this one. Let A belong to A. Let me say suppose A belong to A. So suppose A is in A, then what is the distance between A and the set A? Well, that's 0. Because remember, if I measure the distance between a point and the set, if that point is in the set, then the distance is 0. And 0 is obviously less than delta over 3. So that means that the point A is in GA. Okay, so that means A is subset of GA. And same thing for B. And similarly, for GB. B is contained in GB. Okay, so A is contained in GA, B is contained in GB, GA and GB are open. So we have almost everything. So GA and GB are open. What else do we need? A is contained in GA, B is contained in GB. The last thing we need is to show that GA and GB are themselves disjoint. Okay, The last thing we need to show is that they are disjoint themselves. Maybe I should, to make this easier to read later on, let me kind of outline over here where we're heading. So I'll say we now prove that 1 GA and GB are open. 2, because there's a few things we're doing. A is contained in GA and B is contained in GB, right? So we did that. And the last thing we need to show is that GA and GB are disjoint. So the intersection is empty. So this guy is the first one. And this one is the second one. The third one. I have to show that they are disjoint. So we could do like a proof by contradiction for this one. So let's assume they are not disjoint. Okay, so assume that there's an X in their intersection. Then, okay, so if X is in GA, right? What is the definition of GA? GA, any point in GA, if you are a point in GA, it means that the distance between that point and A is less than delta over 3. So if X is in GA, then the distance between X and A must have been less than delta over 3. Okay. And since X is in GB, it means that the distance between X and B must have also been less than delta over 3. Okay. So now what happens if so now I'm going to, so I know that the distance between X and any point in A is less than delta over 3. And I know that the distance between X and any point in B is less than delta over 3. I shouldn't say the distance, the infimum of the distance. Okay, so what I'm going to do is now choose a point. So let's choose a point A in A and a point B in B such that the distance between X and A is less than delta over 3. And the distance between X and B is delta over 3. Okay, so by triangle inequality, why is it that we could actually find points such that the infimum of this is realized? Because what is this? This is the infimum of dxa where sorry, dx little a, where a ranges over all a, but it's infimum. So if I say that I could choose a in the set A and a B in the set B, such that these things are actually realized, then that means this infimum was actually a minimum, right? It belonged to the set. Um, why that is true, we need to look at again this distance function phi, right? So phi actually gives the minimum. Let me write that as an aside. So side we can, because this step might not be might not be that obvious. We can find, of course, if this step is a bit difficult to understand, you could just use the characterization of infimum, and you could get um something that's like an element in the set A such that the distance between X and A is plus some small number epsilon is less than the infimum of this, which is the distance between X and big A. And this guy I'm saying was less than delta over 3, but this works for any epsilon. So I just need to make epsilon here less than um less than maybe I can make epsilon here equal to something really small like delta over maybe 6. So that means we could do distance of x comma a is less than delta over 3 minus delta over 6. And this is 2 delta over 6, which is delta over 6. Okay, and then the proof will continue from there. Okay, so you could do it this way if you want as well. Right, so what it's saying is that you could essentially just find an element in the set A and an element in the set B, such that the distance between X and A could be arbitrarily small, and the distance between X and B can be arbitrarily small. Right, so it doesn't really need to be delta over 3. It could be anything less than that as well. Right, so by the triangle inequality, yeah, let me take this off. Okay. Because that part might be kind of confusing. So let me actually write it out. So let's do it the rigorous way. So I'm going to be, so let's write it out completely. So now let epsilon be equal to, what did I put it was? It was delta over 6, I think. So let's see if this will work. If it doesn't work, I'll come here and just reduce it even more. By characterization of infimum, there exists an element A in the set A such that if you take, so it's the distance between x and a plus any small amount, so I'm calling it delta over 6, is going to be less than the infimum of the distances xa, where a ranges over all a, and this is of course equal to dxa, that's what I defined it to be, and dxa I said was less than delta over 3. Okay, so this is the characterization of infimum. So this guy here is my epsilon. And from this, I'm going to make dxa the subject of this inequality. So leave it on the left-hand side and dump everything over on the right. So this guy is less than delta over 3 minus delta over 6. Delta over 3 is 2 over 6. So this is 1 over 6, so delta over 6. Okay. Let me call this 3. In a similar way, there exists an element B and B such that, so you could do the same thing, but just use element B and B. You could take the same epsilon as delta over 6, such that the distance between x and b is also less than delta over 6. Okay, so we found an A and a B and B that satisfy these inequalities. Yeah, the reason why I'm doing that is because I don't want to go into the explanation of why that infimum is actually a minimum for this particular function. Yeah, so now we could say by the triangular inequality, let me calculate the distance between this A and B. Right, so this A and B that we found using the characterization of infimum, let me calculate the distance between these two. And instead of going from A to B, I'm going to go from A to X, then from X to B, right, from A to X, and then from X to B, and of course the distance from X to B, oh sorry, the distance from A to X is the same as the distance from X to A. So I'm applying now 3 and 4. So this guy is less than delta over 6. This guy is less than delta over 6 by 3 and 4. Okay, so I'm applying those two. This thing here is equal to 2 over 6, which is a third. So delta over 3. Okay, so the distance between A and B is strictly less than delta over 3. Right, but the distance between A and B should have been what? A is in A and B is in B. The distance between, so A is in A and B is in B. A is in A and B is in B. The closest this distance could be, the minimum or the infimum this distance could be, is delta. So the closest these 2 points, A and B, could be is delta. Here's A and here's B. Right? According to this diagram, or what we start up, the closest this distance could be is delta. But I'm getting this distance to be less than delta over, what was it, 3. Okay, so that's a contradiction, which is a contradiction. since the infimum of these possible distances, the distance between A and B was defined to be delta, right? So if you have 2 points, A from A and B from B, and if you work out the distance between these 2 points, you should be getting something bigger than or equal to delta. But I'm getting something less than delta. Okay, so less than delta. So therefore, these sets were destroyed. GA intersection GB is empty. Okay, and that completes the proof. Okay, so this one was a bit lengthy, but it had a couple of things you have to sort of prove. Okay, and this second part B is saying well, this one is saying if you have two disjoint compact sets, how do we prove that the distance between them is strictly positive? So disjoint compact sets. So part B is kind of straightforward because we've proven a lot of things about these distances. What do you need to recall? Recall the distance between A and B, okay, is equal to 0 if and only if one of these things hold. One, so let me say at least one, right? If and only if at least one of the following holds. Okay, the first one is A and B are not disjoint. If they share a point in common, then the distance between them will be 0. The second one is if A contains a limit point of B. And the third one that could happen is if the vice versa. If B contains a limit point of A. This if and only if, or just if. And this guy is true, then yeah, I think it's if and only if, but we just required it to be if for this proof. Anyway, but I think it's a if and only if statement. Okay, so they're asking us require to prove why is it if we have A and B being disjoint compact sets, why is it that the distance between them was strictly positive, right? That's a fact that we used in this proof. I didn't really sense. We use it to define delta. Right, so we use that in this proof. So now we're going to sort of justify, why could we have done that? I suppose this part should have come first, but oh well. So why is it that this guy is strictly positive? So notice that by definition, what was this thing equal to again? Well, it was the infimum over all points, over the distance between all points DAB, such that A came from A and B came from B. Okay, but this is the infimum over a set of non-negative numbers. The metric DAB is always bigger than or equal to 0. Okay, so what I'm saying is that this distance DAB is always bigger than or equal to 0, since it is the infimum of non-negative points, non-negative numbers. Right? So it's either bigger than or equal to 0. And if you take the infimum of that set, you will get something that is bigger than or equal to 0. What we need to now argue is, why is it not 0? Okay? So it is not 0 because it's not 0 since A and B are disjoint compact. Compact means closed, unbounded, right? So in particular, disjoint closed sets. So any let me write like this. In this way, in this way, we are told that they are disjoint, right? So A intersection B is empty because they are disjoint. And A is closed. A is closed. So if A is closed, A equal A bar. A is closed, A equal A bar. So A bar intersection B is empty. And if B is closed, B is B bar. So A intersection B bar is empty. In other words, any limit point of A is not in B. Any limit point of B is not in A. Right? And A and B share no points in common. Right? So that is what we need in this result. Therefore, the distance has to be strictly positive.